name is Fabien expert. Today we present the work we've conducted with Frédéric Roubieu and Franck Ruffier at the Biorobotics department, which is entitled Interpolation-Based Time of Travel Scheme in a Visual Motion Sensor using a small 2D Retina. And first of all, a short movie, I'm not sure it works. Up. I will go the other way. Up. So just to put some context to my talk, we actually developed a robot, and this robot is using, as the previous presenter said, the optical flow, and it measures the optical flow, the ventral and dorsal optical flow, to control its altitude and speed in this environment. So I have only a few minutes, so I won't say a lot about this robot. But the idea is summarized here. It's actually the control of this robot is based on two intertwined feedback loops that control the altitude and the speed. And we only use one sensing modality, which is the optical flow. Here, circled in red, you have the eye of the robot, which is looking upward and downward. And the problem we had with this robot, as you saw, it's further to the end of an arm, because we cannot compute the optical flow in every direction. And that's what we want to be able to do in a small eye, be able to have information about all the environment in every direction. And that's what we started to do on this retina that we call APIS, for Adaptive Pixel for Insect-Based Sensor. And this has been developed with another lab in Marseille, which is called CPPM. And this retina is composed of Delbrück type autoadaptive pixel. And the property of this pixel is that they automatically adapt to the background illuminance. And so we chose on this retina 3x4 pixels that we have on the board on the right. And with the electronics, we want to be able to compute the optical flow, which is also an angular speed with this retina. The way we do that is by using what we call the time of travel scheme, which is inspired by the electrophysiological findings on the fly eye. And the idea is quite simple. We actually have two pixels here, which are separated by an interceptor angle delta phi. And when a contrast will cross these two pixels, here, for example, it's a black to white contrast, so we have an increase in the voltage response of the two pixels. And due to the angle between the two pixels, we'll have a time delay between the two signals. So that's the basic idea of the sensor, which is quite simple. We actually convert an angular speed into a time delay, and we can measure this time delay using classical electronic. And this time delay, the angular speed will be equal to the interceptor angle delta phi divided by the time delay delta t. So here on this example, we can measure delta t with a perfect resolution, for example. So in case we do that electronically, we'll need to have a very important sampling frequency. And this is the problem for our sensors. If we have a very important sampling frequency, we need a lot of computational power to do that. That's why we optimize our algorithm by using only a linear interpolation. So here we have the two same signal, and we can assume that we have a sampling frequency represented by the blue points. And as you can see, if we use this low sampling frequency, we will have a bad measurement of the delta t delay due to the fact that we only will take points a lot after crossing, for example, a threshold. What we want to be able is to measure the time delay delta t separating the two signals with a good resolution. And to do that, we actually want to be able to measure this time t1, for example. And to do this, we linearly interpolate the signal when we cross a threshold. And from that, we can determine with a very good resolution the time t1. And the same way, we can determine the time t2. And then deduce the real time delay between the two signals with a resolution that is a lot better than the sampling frequency we're using for our processing. And from this processing, we chose to use that on our retina and to compute every possible two-sensor local motion sensor in both directions and in both ways. And the idea at the end is to take the median value from all the angular speed measurement in one direction and the median value of the opposite direction and then take the maximum value. And from that, we can obtain the direction and the magnitude of the angular speed for horizontal motion. And the same way, we can do that for vertical direction, obtain the direction and magnitude of the angular speed. And we tested that on a test bed, which is quite simple. We have the sensor with the electronic board placed in front of a wallpaper, which is moving thanks to two actuated drums. And due to this motion of the pattern, it creates an angular speed, omega wall, seen by the sensor. And all these experiments has been done at about 200 lux indoors, so that's the kind of luminance you will have when you have a window open in a room, for example. And the first part of our work was to find the best sampling frequency for our experiment. What we call a good sampling frequency is actually a frequency that will not take too much computational power and still give a good and accurate measurement. So we did that in simulation, but from real signal. And we did that for horizontal and vertical motion. And for example, we did that at 100 Hertz. So here you see in red the theoretical angular speed of due to the motion of the contrast. And in blue or in green, you see the output of the sensor. And to compare the performances, we determine the dispersion of the data, which is defined as the standard deviation of the difference between the theoretical and the measured angular speed. So we did that at 100 Hertz, 200 Hertz, and 500 Hertz, because usually before we were using 1 kilohertz or 2 kilohertz to have a good resolution. So we wanted to go to smaller value, but we knew that we couldn't go less than 100 Hertz. And what we noticed is first that the dispersion of the data decreased when the sampling rate increased, which is logical due to the fact that the linear interpolation is getting better and better when we increase the sampling rate. But what we concluded also is that actually 200 Hertz is a good trade-off for us between the accuracy of the measurement. We had a dispersion smaller than 20 degrees per second, and the computational load of the microcontrollers that was limited compared to previous sampling frequency. That's why we've chosen 200 Hertz as the sampling frequency for further experiments. And we did the same experiment, but now with the processing embedded in the target. Everything was in the target board I presented. And we obtained even better measurements than what we were expecting, with a dispersion of 13 degrees per second. And we also measured the refresh rate of the sensor, which corresponds to the number of measurements per second. And we obtained nearly up to 100 Hertz, which is really good for us for robotic application, for controlling a robot, like I presented at the beginning. And as a comparison, we did the same thing, but at 1 kilohertz, but without interpolating the signal. So of course we obtained better results, but they're only really slightly better, around 10 degrees per second of dispersion. So the conclusion was that we had accurate and highly refreshed measurement of the angular speed thanks to our processing. And the main advantage was the computational load was strongly reduced. From 200 Hertz we had 10.5%, whereas at 1 kilohertz we had 44.2% in average. So we divided by more than 4 the computational load of our microcontroller. So that would be the conclusion. We obtained basically the same accuracy with a sampling frequency divided by 5, and we reduced or divided the computational load by more than 4, which would allow us to multiply by 4 the number of local motion sensors we could have in the same target, which means that actually we could use optical flow extraction in a wider field of view with more pixels. And that's exactly what we want to do in the future. We plan to embed this processing into a curved artificial compound eye that we are currently developing in the framework of the European project COVEX. And the idea will have that we have a lot of pixels and a really big field of view like the compound eye of the fly. Just a few words about that. Next year will be held in Tübingen in Germany, a workshop about compound eyes dedicated to this sensor in particular. We'll have nice speakers and sessions, so if you want to attend, I encourage you to check on the website for more information. Thank you.